morning, I'm Nori. We are a teammate and we're going to do motion capture for runners. I'm Nori, I'm an electrical engineer.
I'm Chen Li, I'm from electrical engineering.
I'm Ji-Cha Lu, I'm an electrical engineer today.
Alex, electrical. And Dan Zelenskis, electrical.
Blake Vance, also electrical.
And we're sponsored by the Air Force Research Laboratory, as well as our facilitator is Dr. Agnew. What we're going to talk about today is a little introduction of what motion capture and what we're trying to do, as well as our proposed solution and design concept that we've come up with project components that we have chosen, as well as testing, risk analysis, and project management stuff.
I will do a brief introduction of our design. Many people enjoy workout, but a few of them have knowledge of the efficiency of how they are doing their exercise. And our design is to help them improve their running efficiency. The running efficiency is directly proportional to their posture. Under different running conditions, the running posture changes significantly. So we want to capture their running motion and do some post-process to analyze the running motion. I will give you some example of different postures. For example, when you are running up hills, you need to use good use of your arms and left your knees so that you can run up. And when you are sprinting, the frequency of each running step increases, so you get the acceleration. Actually, it's an interesting field, and there are some research that was done before, and those research focus on the measurement and analysis using three-dimensional accelerator and gyroscope. We will do the similar things using similar device that has both of the two functions. As mentioned before, our overall objective is to improve the running efficiency. So the first objective is to capture the running motion by choosing proper sensors, because it's hard to tell which running motion is correct and which one is wrong, and it's hard to tell the difference between the wrong and the difference. But with the proper sensors, the running motion can be transferred to some numerical data, which can be analyzed later. The next objective is to develop an interface that communicates the sensor and also it communicates the processor. This is the important part, because it transfers data and it receives feedback from the processor. The sensors are directly connected to the controller, so the controller will be body worn. And one of the important features of our design is real-time feedback, so that the runner can get feedback when they are running, and they can correct their running motion immediately. So that requires the software and our external processing PC have real-time processing ability. And the design our team did is not limited to the running motion. So the last objective is a further objective in the future, which is to understand the flexible structure on aircraft and spacecraft. Because the analysis of running motion and analysis of this kind of objective have some kind of similarities. So it can be also applied to many other fields.
I'm going to go over some of the benefits of our system. The direct benefit of this is that it helps you maintain proper running form. And with proper running form, increases your overall running performance, and then also if you run properly over time, there's less chance of injury being. And also, with the real-time feedback for the runner, this allows for immediate change as opposed to delayed change, so they can change their form right away. With our comparison software, we have a elite runner perform their running to provide a baseline model that you can look at to compare. And the last benefit is that this motion analysis and feedback is kind of general, and it can be applied to other systems using the same technology that we use.
Okay, so our proposed solution is that we're going to have sensors that will be attached throughout a bodysuit. These sensors that we're going to use are called inertial measurement units, or also known as IMUs. They are accelerometers and gyroscopes, as well as magnetometers. Depending on different applications that you want to use, there's different IMUs. So these sensors are going to be directly wired onto a body-worn microcontroller, and this product will be used for treadmill purposes due to wireless constrictions. And this body-worn microcontroller will perform preliminary data processing as well as timestamping. In order to utilize real-time feedback, timestamping is necessary because we're going to have multiple data points coming from multiple sensors, and they need to be matched with their corresponding time. Then the body-worn microcontroller will wirelessly send the output of that microcontroller to an external PC, and this will do the primary processing as well as comparison software. Our wireless communication is going to be X-speed, and we're testing out either Wi-Fi or Bluetooth as well. And the real-time processing will be done on an external PC, and the comparison software will be written, and our baseline model is going to be an elite runner. We're going to have some MSU cross-country or track runners to use our product. And lastly, we are going to have real-time feedback. So the runner will have a body-worn indicator, and it'll be a visual indicator to show if they are running properly or improperly.
So these are some specifications that we have to take into consideration when choosing the concept that we're going to go with. So with the battery, we want the size to be as small as possible because it will be on the person, so it can't impede their running form. But it also has to be long. The battery has to have enough power to do multiple testing runs. And then for the sensors, we want an IMU with the most number of axes, so 6 or 9. And the more axes you have, the better accurate you can model location and movement. Also with the sensors, we want to keep power consumption to a minimum. Sampling rate, we want to have high enough so it can accurately detect the motion. And with the sampling rate, we can also decide to, if it's movable, to change the sampling rate lower to increase that battery life. And again, with the sensors, we want the size to be kept to a minimum because this will be attached to the person. For our wireless, the bandwidth needs to be high enough to transfer all the data because there will be 5 sensors that get data collected by the microcontroller, and that needs to be transmitted, and then also the range needs to be far enough to transfer to the PC nearby. And lastly, the cost needs to be kept to a minimum.
All right, so I'm going to talk a little bit about the actual components that are going to be used in our design. To start off with, we're going to be using IMUs, like everyone has said so far, which are inertial measurement units. They're the sensors that are going to be placed around the body. We're going to have multiple sensors that will all be communicating all at the same time. So that it's actually collecting all the data, and all that data is actually sent from the IMUs and directly wired to the Arduino microcontroller. Now the Arduino we're using could actually be either the Arduino Uno or the Arduino Due or Duo. I can't remember which one actually is, I think it's Due. But the Due actually has a higher processing power and actually more memory compared to the Uno. The problem is the Uno actually, it has more support, and since it's been out for a longer time, more people know how to use it, and it has a lot more universal parts compared to the Due. Once all the data is actually sent to the Arduino, like Nori had said, it actually has to all be synchronized too, using the synchronized clock that's actually on the Arduino. That way all the data that's coming all at the same time, you can tell which data is coming from which sensor, otherwise it's just a big jumbled mess. So then after that, we have what's called X-speed or Zigbee communication. X-speed is actually the brand name. So the X-speed communicators are actually put on top of what are called Explorers. And the Explorer actually just sits right on top of the Arduino microcontroller. Now, the X-speed communicator is wireless, so once all the data is sent to the Arduino collects it, and all that data is sent wirelessly through the X-speed communication from the Arduino to our external PC. Now, on top of the Arduino as well is what are called shields that goes along with the X-speed communicator. Now, because the Arduino has a limited amount of memory, and you're collecting data continuously from all the sensors over and over and over in a constant loop. And you have a micro SD card that's actually placed into the Arduino as well to actually hold that extra data. The data is held on the SD card, and while it's looping, it's continuously erasing previous data, so that data is constantly being erased and sent to the PC at the same time continuously over and over and over, so you can constantly collect data from all the sensors and you won't run out of space. And next, you also need to be able to program the Arduino microcontroller, because the Arduino isn't just going to work on its own without its own programming software. So since we're using multiple sensors, the bus that's on the Arduino is called the I2C bus. And we need to configure that using the programming to be able to accept multiple signals coming in simultaneously at the same time. And then you also need to set up the Arduino to communicate with the XP device so that it's able to transmit everything to the PC wirelessly. And then after everything is sent wirelessly to the external PC, we have what we're going to use for PC software, where it's going to import our data from the Arduino and actually compare all that data using our comparison algorithm that we're going to write either using MATLAB or LabVIEW or processing. And processing seems to be the best choice just because processing is an open source software that is used with a lot of Arduino microcontrollers in the past, and there's a lot of support for it. So, and like I had said, this is just an overall block diagram of basically how our design is going to work. So you have all the sensors that are going to be placed around the body, and they're going to be wired directly to the Arduino microcontroller. We're using a wired bodysuit because that way you can limit the amount of data that's lost. Because if you're using wireless devices to communicate with other things, there's always a chance of data loss and packet drops and so on. So once all the data goes to the Arduino and it's time-stamped and synchronized, the Arduino is wirelessly connected to the external PC using XP communication. And once everything is run through the PC software, you actually send the data from the PC through another XP communicator or wireless back to our feedback controller, which will give our runner real-time feedback either via LED or LCD screen.
So I will be covering the testing plan as well as the risk analysis of our design project. There are four main parts here as shown. There are sensors, Arduino board, communication or interfacing, as well as the software testing. So for the first part of sensor testing, the priority here is to make sure the consistent data capturing by each individual IMUs. In order to test it, we will have different team members to put the sensors on their body, and then we will use the software from Autodesk called Motion Builder. That way we can see the data that's being captured by each IMU sensors, as well as the software is capable of replicating movement of human body. That kind of gave us a visual realization of the data. The second part is the Arduino board. The Arduino board, data transfer-wise, Arduino board here in our design serves as a router, which means that we don't want anything to be changed, added, or modified during the process when the data passes through the Arduino board. Also, the Arduino board needs to be properly time-stamping all the data, which means that it needs to be synchronized all the data to a common clock signals. And the third part is the communication or the interfacing. A typical path of our data transformation is from the IMU to a Arduino board via wire, and the Arduino board to the PC, then PC back to the indicator that's on the user's body wirelessly. And among the three data transformation paths, the wireless path between the Arduino board to the PC is critical, and that actually is the fundamental for the later on running form comparison analysis. I will elaborate more on that when I talk about the risk analysis on the second slide. And in order to test the efficient communication, we need to make sure there's no noise even coupling to the system. If there is, we need to figure out a way either figure it out or find a better approach to wirelessly transfer all data. And the last part in the communication is the easy understood feedbacks. One of the main features of our product is to give the user real-time feedback of their running form efficiency. So we got to make sure the feedback signal is sent to the user in time, and it's very easy for them to understand. The last part in our design, our testing plan, is the software testing, and the main issue here is on the PCM. So when the data transfer to a PC, we will use both the software that's counted as the IMU as well as Arduino board. By using these two software together, will be able to process the raw data that's collected by the sensor to an organized data matrix that's readable by the later data processing, data comparison software, which Plans uses probably processing or MATLAB. Also, to summarize the testing plan, we need to make sure every component in our design project is functioning in a consistent base. Now let's move on to the risk analysis of our design project. There are many bullet points shown here. I will zoom more into the power consumption, the continuity of the data acquisition, as well as the transmission of the data. So first, the power consumption of our constraints here. It's actually the biggest concern and constraint to our development project because all the IMUs are directly wired to our Arduino board, and they are all powered by the central battery that's on the Arduino board, and both the Arduino board and the sensor is continually sensing the data and transferring the data, which means they require a lot of power. So the limited power here really constrains our project development. And the second point here is the continuity data acquisition, which here we mean the memory limitation, because the IMU is continually collecting the data and transfer the data to the Arduino board, and the Arduino board itself has very limited memory storage, so the Arduino board itself needs to be programmed in such a way that it temporarily hold this data points, and when the data is transferred to the PC, remove this memory storage for later uses. The third part is I want to talk about is the transmission of the data. Since our using the IMU is basically utilizing the accelerometer, which means the data information basically contains the acceleration information. So when we want to get the position information out of the original data, the data points need to be integrated twice. So even a small error that's being introduced during the transformation of data will be magnified exponentially due to the twice of integration. And then there are some other things here I didn't go into detail because they are very intuitive, like the synchronization. Small mismatch or misaligned data in the data matrix will result in a inaccurate running form comparison, which in the end results in a inaccurate feedback to the users.
I'll just go over some of our team members' roles during the duration of our project. I'll be working as the presentation prep, along with the suit fabrication, making sure that it's user-friendly and the sensors are placed in proper points around the body. I'll also be the demonstration person, make sure our demonstration software creates an accurate 3D model of the data that the IMUs are transmitting back to the Arduino. The Chow will be in charge of documentation prep. He will also be in charge of testing and data analysis, making sure that the data that the IMUs record is accurate and is easily understood by the Arduino and the PC. Alex will be working as our webmaster and writing our comparison software, making sure that the data from the elite runner is accurately compared to the data of the average person running. Nori is our manager, and she will be in charge of the data comparison data collection, going out and finding an elite runner and making sure the form is proper and that the IMUs record this proper form. She will be also in charge of the Arduino software, making sure that the software that takes on all the IMUs data is properly transmitted to the PC. Chen Li will be in charge of presentation prep as well, and the wireless communication system, making sure that the Arduino is in a range that is acceptable for Arduino and our PC. And Dan is in charge of the lab coordinator, and he is the interfacing technician, making sure that all parts are interfacing correctly and that no data is lost.
All right, so this is just a quick overview of our budget. As you can see, most of our expenses are coming from the IMUs that we're buying, especially since we're buying at least 5 of them to begin with, as well as the Arduino Due and the Arduino Uno. Now, this totals to about $700, which is actually above the normal limit for most teams' budgets, but we were actually given a rather generous amount of money to work with. So a lot of the parts that we actually ordered on here are just extras, just other things that we can use to test on our product, just to make sure we have multiple solutions to implement our design.
This is just a little schedule overview of our project. It's broken down into like 4 different topics: fabrication, software, interfacing, and testing. The majority of our time spent will be on the software and interfacing. We have to write our comparison software and make sure that this is accurately compares the elite runner's data to the average runner's data. However, the most of our time is going to be interfacing, making sure that all the parts of our system are properly communicating with each other. If there's one minor error, it's going to mess up all down the line. So you got to make sure that at the beginning IMUs interface with Arduino, the Arduino onwards.
So in summary, our objective is to capture a runner's motion. In the problem statement, it was very vague, so it's a really open-ended project. So we have come up with our proposed solution of the bodysuit with IMUs placed throughout the body. And the Arduino, which will be the body-worn microcontroller, will receive the data and transmit to an external PC. And the analysis will be based from a elite runner, and we will have to write a comparison software with that elite runner to see if the runner is running properly or improperly. And then with the real-time feedback, that the runner will get immediate feedback via a body-worn indicator to show if there is a proper or improper form in one of their limbs. And that's it.
Thank you. Are there questions?
I have one. How are you guys going to take speed into account for a proper running form?
Well, based on the type of feedback we're doing, there's a lot of variables that we actually have to take into account. I actually talked to Professor Mason himself just to see what he would say, and he said to simplify our feedback to things such as whether you're leaning forward too far, leaning back too far, maybe how far apart your stride length is, things like that. You'd have to simplify your feedback. Otherwise, like Mike was saying, if you're trying to integrate position or from an accelerometer, you're integrating that data over and over, or at least you're integrating it twice. So if you have a small error in your data at all, you're going to integrate it twice, and the position is going to be way off. So there's a lot of variables that go into it. So we're basically simplifying our overall feedback.
Because you guys are having your runner stay on a fixed treadmill, did you guys consider using cameras and do like image processing for movement?
We were, but I think the whole point of this project was to use these motion sensors, not a camera, because like the Xbox Kinect does exactly what you're talking about. To test to see if our IMUs are working correctly, we will use this Autodesk Motion Builder, which is like the Kinect, to see when there is improper running form that our comparison software and our IMUs are working correctly. So we will use that as a testing analysis, but not for our project because they want to use something other than a camera.
Yeah, just to add to that, like the IMUs, like the Air Force are planning to like maybe use it on like the ends of wings, or they don't want to use a camera. They want to just research into like the IMU technology a little more, so they could possibly use it down the line.
Question. So what's the sampling rate on these IMUs, and what sampling rate do you think you'll need?
I think the sampling rate was at least 1 kilohertz or higher. You do definitely need a high enough sampling rate to be able to get all the data points, because otherwise their limbs are moving too fast, their body's moving too fast, and suddenly you have inaccurate data. So the sampling rate we made sure was at least 1 kilohertz. The biggest concern is actually whether the XP device, which would be sending all the data from the Arduino to the PC, had a high enough sampling rate to be able to accommodate all the sensors at the same time, but that should as well. So.
Any other questions? If not, thank you.